So unimolecular nucleophilic substitution. This is also known as the Sn1. Right? So unimolecular is the 1, nucleophilic, that's your N, substitution is your S. So this reaction is really an interesting reaction. Now there's two ways that you're going to see this, and I'm just going to label this here as simply flavor number 1. Okay, so what we're going to start off with here is this. We're going to start off with a substrate. All right, so let's make a couple notations here. Here is your substrate. Notice, by the way, that it's a tertiary alkyl halide. Okay. And then the other thing I want to remind you of here is that iodide is a good leaving group. So we'll see in this chapter, if you don't have a good leaving group, then there's really not going to be a reaction here. All right, so let's go through this. So step number 1. Notice here that the steps in this reaction are reversible. So step number 1 is that our leaving group is just going to take its electrons and run for the hills. All right, so what we're going to get here for this intermediate is 1, 2, 3, and a plus charge right here. Now what do we have? This is a carbocation, and the carbon that we have right here, that carbon is sp2 hybridized. So just make a note here, we have a carbocation, right? sp2. Now it turns out that the stability of this is going to be very important. And I just want to make a note of that down here below. So really pointing this out here, the stability of this intermediate, or the ion, is important for this reaction. All right, and I'm just going to tag it on up here to this statement, just like that, right? Now, that's our step number 1, so let's just make a note over here. Here's your step number 1. It turns out that that is your RDS. That's your rate determining step. Right, now, what happens next? Step number 2. So step number 2, we're going to have some type of nucleophile come in. So for this, I'm just going to write NuC, right? And we'll just put like a minus right there for this. And let's make a note here that this is step number 2. So then our nucleophile comes over here and makes a bond with that carbon. So what that's going to give us here is our 3 carbons now attached to this nucleophile. Other thing to point out is that that carbon right here is a potential stereocenter. So we might have to worry about chirality there. Now it turns out that most of the time in these Sn1 reactions, our nucleophiles don't have charges. So I want to show you flavor number 2 down here below. This is what you'll see most of the time. So here's our flavor number 2, guys. All right, so for this one, same first step. So we're going to go through here. Here's our iodide. That's your substrate with a good leaving group. And the first step of this reaction, remember, is that we have our leaving group take off. So that's your step number 1. And that, remember, is your rate determining step. So put a plus charge there, just like this. Most often what we have here is we have weak nucleophiles, weak bases. And very commonly we use water or we use an alcohol. So I'm going to do this. Let's make a note here. Here's our step 2. And for this, let's add R OH. So here we'll just use a generic alcohol. So ROH there. And there we have it. So then step number 2, this comes over and attacks that carbon. So then what you're left with is this. There's your 3 carbons, but now we're connected to this oxygen atom right here. Okay, so that's our oxygen here. That oxygen is connected to an R group and an H. It's one of the lone pairs of the oxygen that makes that bond to carbon. So we have 1 left over, and that leaves us with a plus charge right here. And then the third step of this reaction, so step number 3, is we do a deprotonation. And to do that, we use the alcohol here. So we're going to take a set of these electrons, come around here and grab this H. And then that set of bonding electrons would come back down to your oxygen. So then you get 1, 2, 3 carbons, but now we have an O and an R group over here just like so. Right? And we don't often write this, but technically you get an ROH2 plus if you want to put that in there. But most of the time we leave that out. Okay? So let's take a look at the reaction energy profile for this. Notice that this has 3 steps, and that's what I want to look at down here below. So this is the reaction energy profile here. Remember, over on this axis we have our energy reaction coordinate down here at the bottom. And in this case I chose a bromo group to be on this. So step number 1, right, is the loss of that leaving group. That forms that carbocation. So here's our carbocation, right? Next, what happens is we come in with step number 2, right? Here's an OH2 plus, so this would be plus H2O, right? So you get this protonated form, and then at the end you lose your H on that to become just your OH there. Couple things to point out to you. That first step, and I left the little arrow in here, this has the largest activation energy, right, compared to the other steps. Right, so this would be the next activation energy here, and then this would be, right, your third activation energy. So that large activation energy is why that first step is your rate determining step. It's your RDS. It has the biggest, it's the biggest activation energy, and it's the largest barrier to the reaction continuing. Right? So the other thing that I want to point out to you guys might not be super obvious right now, but notice that that step is endothermic. So our transition state is right here, and it lies closer to our carbocation. That's a Hammond postulate thing. Right? So what we can say, and I'll just make a note up here, all right, is that our intermediate, well, let's just say this, our transition state. So our TS, it simply lies closer to that carbocation. Right? And because of that, the transition state looks more like a carbocation. So therefore, right, any of the factors that help stabilize carbocations are going to help this reaction proceed at a better rate. So factors that stabilize the carbocation will help this reaction, right? So if you can have a more stable carbocation, then you'd pull that activation energy down lower, so the reaction would proceed faster then. Okay. So what are some of those factors? Well, remember from previous lectures, we have things like R groups. Remember, the R groups are electron donating. So the more substituted that intermediate is, the more stable it would be. Other thing to point out here, remember here that the rate law for this is unimolecular. So the concentration of the nucleophile doesn't matter at all. It's the concentration of the substrate. So the substrate identity is most important because that first step is the rate determining step, formation of that carbocation.